Aspect of physics called the transformer. The transformer. Then you've seen transformer even in movie. You see movie title bearing the name transformer. So in conceptual physics, what is the meaning of a transformer? In IGCSE physics, what is the meaning of a transformer? What is a transformer and what does it do? Because this device is very necessary for the distribution of electricity. For transmission and distribution of electricity, this is one of the super devices that is necessary or needed to distribute or to transmit electricity from the power station to substation and to our houses. So on that note, we need to know the meaning and the usefulness of a transformer. We start by saying a transformer is an electromagnetic device. So we take that point that a transformer is an electromagnetic device. So I will write only an electromagnetic. Okay, this is the first important word. What do we mean by electromagnetic? Meaning it combines the quality of both magnetism and the quality of electricity together. So we say a transformer is an electromagnetic device. So that's the first thing we should understand, that a transformer is an electromagnetic device. If that is so, what does it do? That is used for stepping up. So my first point is that a transformer is an electromagnetic device. My second point about transformer, or my second point to note about transformer, is that it's used for stepping up and stepping down voltages. Meaning, if we produce voltage or EMF in a power station and we want to transmit it to a long distance, what we need is that we need to raise the value so that we will not lose the voltage over a long distance. If we produce, for example, if we produce 11,000 voltage, we need to step it up to 440,000 voltage. We need to step it up to about 440,000 voltage. The device we will need to raise the value from 11,000 to 440,000 is called a transformer. So it's used for stepping up, not only stepping up in power station. When we get to substation, where we need the small value of the voltage, we need to bring the voltage down because the 440,000 is too huge. We cannot use in our home. Remember, the voltage we use in our houses is just 230 volts. It's just 230 volts. Okay, for a transformer that is using 50 hertz frequency. The voltage that is needed in our home is just 230. So imagine you produce a voltage of 11,000 volts in your power station, and you need to distribute across a country, across your entire country. So you need to step it up because 11,000 volts to travel throughout a country will be diminished or will be lost. Most of it will be lost. Probably before you get to the end game, you will not have enough volts. So what a transformer does is that you key in this value to a transformer. You put this value to a transformer. Let's show a schematic of a transformer. Okay, you key this value to a transformer. Okay, let me show a schematic of a transformer. Okay, before this. Okay, you key this voltage into a transformer. It comes out with a higher value. Okay, this is a schematic diagram of a transformer. This side is the primary side of the transformer, while this side is the load, or what we call the secondary side of the transformer. The load side, here you put the load. Maybe it could be a resistor, it could be any load, a bulb, whatever you are powering. This is the secondary side of a transformer. This is the source voltage, where you have your voltage applied in the primary. Okay, but it must be an alternating voltage. So this side is the primary. Okay, this is my primary side of the transformer. So for primary, I just write PRY. Okay, for primary side, and this side is my secondary side of the transformer. Secondary, I write SEC, secondary side of the transformer. Now what the transformer does is that you feed in a voltage, it will step it up. It's either it steps it up or it steps it down. If it's a step up transformer, meaning we need more windings in the secondary side. So meaning I need more coil here, more coiling here. If I want it to step it up, I do more coiling here, more coiling here. Okay, then the voltage that is fed from primary will be step up, if we have more coils on the secondary side than on the primary side. Are you with me? Okay. Okay, so we say a transformer is an electromagnetic device. That's the first statement we make. We say a transformer is an electromagnetic device. That's the first statement. It's a device, electromagnetic device. That is what? That is used for stepping up voltages and stepping down voltages. Either raising voltages to a higher value or bringing down voltages to a lower value. With the third point to make is that the operating frequency will have to remain constant. Operating frequency, so I'll just write frequency, no need to write operating frequency. So with the operating frequency remaining constant, meaning the value of the frequency has to remain same. You don't have to be changing the frequency, okay, of a transformer. In many countries, we use two frequencies. There are two different frequencies that we use for transmission. So some countries stick to the 50 Hz frequency constant, while some countries stick to 60 Hz frequency. Now we'll give example of some countries that use 50 Hz and example of countries that use 60 Hz. Now countries that use 50 Hz, they use 230 voltage. Countries that stick with 50 Hz frequency constant value, 50 Hz frequency, the voltage that they use in domestic voltage is 230. But for countries that stick with 60 Hz, for countries that are using 60 Hz frequency, their voltage is 110. They use 110 voltage. Okay, like Japan. Countries like Japan, countries like Japan, they stick with the 60 Hz frequency and 110 voltage. UK, they use 50 Hz and 230, I think so. Most African countries like Nigeria, they use 50 Hz and 230 voltage. Malaysia use 50 Hz and 230 voltage. Okay, some countries, I think United States, they use 110 voltage and 60 Hz. Okay, so it depends. If you're using 60 Hz, your voltage, domestic voltage will be 110. So it's okay depending on what the country decide to design or decide to use. So the job of a transformer is that if it's a step-up transformer, it will raise this value, probably maybe to a higher value in the power station, to maybe about 400,000 voltage, to about 400,000 voltage. So from 11,000 voltage that is produced in the power station, you know the production. When if you depend on what you're using on your power station to generate electricity, you just use steam. For example, if you're using steam, but you use gas to heat a steam, water to turn to steam, you use the steam to turn the blades of a turbine. The turbines are connected. The turbines, the rods of the turbines are connected to the shaft of the generator. As the generator rotor rotates, then as it rotates, EMF will be induced according to Faraday's law. So that induced EMF is the voltage that we're talking about. That voltage is fed into a step-up transformer. The voltage that is produced, let's assume in the power station we're producing 11,000 voltage, or we produce 11,000 voltage, this 11,000 voltage is fed into a step-up transformer, and the value is raised up to 400,000 voltage, which is now fed into our transmission line to be transmitted across the country. Okay, as we get to other substations, we put other step-down transformer to bring out the value of the voltage till we get to our home, where we can subsequently reduce it to 230 voltage. So these are the three things we've talked about transformer. We say a transformer is an electromagnetic device. That's the first point. So the second point is that it is used for stepping up and stepping down voltages. Okay, we have to write the voltages. It is used for stepping up and stepping down voltages. It is used for stepping up and stepping down voltages. The third point to know about transformer is that it has operating frequency that is constant. Okay, with operating frequency remaining constant. With operating frequency remaining constant. Now that constant value could be 50 Hz or 60 Hz, depending on which value a particular country has designed to or decided to use. Okay, so now let's go further than this. Let's take a look at the transformer in its own set. We said the transformer consists of the primary coil, which we have shown. You see what they've shown here. What they've shown here is that it has a soft iron core, COR, soft iron core. Okay, and that the voltage we are going to apply is going to be an alternative voltage or alternative current. That's why we use alternative current, so that it can produce a changing magnetic field. So the next thing to describe is that how do we now link the voltage on the primary side to the secondary side? This side is the secondary side. These are coils. These red ones are the coils. You can see the coils on the secondary is more than the coils on the primary. Okay, here is where you connect to the source, the AC source, alternating current source in the primary. This is a soft iron core. In my diagram, I use line to show the soft iron core, just a line to show it. Okay, just line. Just this line to show the soft iron core. Now these are the coil. These are the coil. Coils in the primary side. These are the coils in the secondary side. Okay. Remember, this one is the real life transformer. This is the real life transformer, how it looks. Okay. This is just a diagrammatic representation of a transformer. Now we say the primary side. This primary side has fewer coils because this is a step-up transformer, and the secondary side has more coils because we want the voltage produced to be larger than the voltage that is being imputed in. The input voltage to be smaller than the output voltage. We want the output voltage to be bigger. So you make more turns here. You make more turns of coils here. Now, there's a magnetic field. Every time we connect to AC source, to a current source, current flows through this wire, it will produce a changing magnetic field. Why is it a changing magnetic field? Because it's an alternating current, AC current. Alternating means changing. So it will produce alternative magnetic field or a changing magnetic field. Why we don't use a battery for transformer is this. If you use a battery, it will not produce a changing magnetic field or flux. It will not produce a changing magnetic field. And in transformer, we need a changing magnetic field so that the field that is produced in the primary coil side will be linked through the soft iron core, to the secondary side. So that it will be linked through the soft iron core to the secondary side. So that's why we need a changing magnetic field. If you use a DC current, like you connect this to a battery, it cannot produce a changing magnetic field. It cannot produce what? A changing magnetic field. It will only produce, it will not be a change, it will not be alternating. The magnetic field will not have a sinusoidal behavior. It will not be able to travel from here to the other side, to the secondary side. So that's why we use an AC current here. When we connect this to an AC source, alternating current source, it will produce a changing magnetic field in these coils. Okay, that changing magnetic field will be linked to the secondary side. Will be linked to the secondary side. Will link itself to this side. Okay, so the EMF induced here is linked to the secondary. So the magnetic field that is produced is linked to the secondary side, so that when the magnetic field reaches the coil at 90 degree, At 90 degrees, it will induce EMF according to Faraday's law. To induce EMF, which is called the voltage. And that voltage is the output voltage that is harvested or harnessed here. That is harnessed here. Is the output voltage that is harnessed in this secondary coil. Okay, if you want a step down transformer, you make more coil on the primary than the secondary. Once you make more coil on the more windings on the primary side than the secondary, you have a step down transformer. But the moment you have more turns on the secondary, you have a step up transformer. Is that okay? So that's the first thing I want us to look at, or I wanted to explain. Okay, so this is a transformer. What type of metal we use in designing a transformer is iron, not copper. We use iron for the core. Okay, you can use copper wire for the coil, copper wire for the coil, iron for the core. You must take note of this. You must take note of this. They are always in the exam, especially in multiple choice questions. They can fool you like this. Which of the following is used in designing the soft core? Which of the following is used for designing soft core? Which of the following metal is used for the core? So we say transformer is an electromagnetic device, right? That is used for stepping up and stepping down voltages. It's used for stepping up and stepping down voltages with the operating frequency remaining constant. The frequency remains constant. Okay. Then I mentioned that some country the frequency is 50 Hz. If they use 50 Hz, then the voltage will be 230 in our homes. And then we say transformer, if it's a step up transformer like in the power station, you feed in 11,000 volts, you can get the output to be 400,000 volts. You can step it up all the way to 400,000 volts. So this voltage is fed into our transmission line and be transmitted to our from different state to different state. And on getting to substation, this voltage is stepped down to a reduced value according to the use of that place. If it's industry, we can step it down to 415 volts for industrial uses. 415 volts. For our homes, we step it down to 230 for our home usage. Okay, so that's a brief one, although you heard, but you just needed to see. Now let's take a look at the transformer. We said the real transformer consists of the primary coil, these ones, this red one, the primary coils, and the secondary coils, and then the soft iron core, this one, this body, the soft iron core, and the soft iron core. Is that okay? Okay, so this is a transformer. We've looked at this. Then we said in the exam, they might ask you which metal is used for making the core. It's iron. The metal that is used for making the core is called iron. What about the coil? The coil is copper. You can use copper to make the coil, but you use iron to make the core. You use iron to make the core. So it's always, you take note. You take note. Okay, now let's take a look at the operation of a transformer. We already said that an alternating current is what we supply to the primary side. I've explained that in the primary side, we have to supply an alternating current. Why do we have to supply an alternating current to the primary side? So that we can continuously and continually produce a changing magnetic field. So that we can produce a changing magnetic field, an alternating magnetic field. Why do we need a changing magnetic field, not just a magnetic field? So that we can link it to the secondary side. So that it can be linked to the secondary side. If it's not a changing magnetic field, it cannot be linked to the secondary side. Okay? So we need alternating current, a changing current to produce a changing magnetic field. That changing magnetic field will be linked to the secondary side, and once that field cuts across the coil at 90 degrees, an EMF will be induced. EMF, remember I say is voltage. EMF will be induced. Now the EMF, electromotive force, is the voltage that is produced, and which is now used or sent for further processing or further usage, depending on why we do what we are doing. So we say a transformer needs an alternating current. We don't use a direct current for transformer. We don't need a direct current for transformer, because direct current cannot produce changing magnetic field. A direct current cannot what? produce a changing magnetic field. Now the current is continuously or continually changing direction. Yeah, the current is continuously or continually changing direction so that it will produce a changing magnetic field. So that it will produce a changing magnetic field. It does not produce a changing magnetic field, we can link it easily to the secondary side. So this is just the operation of transformer. And then EMF will be induced once the field cuts across the windings at 90 degrees. Once the field cuts across the winding at 90 degrees, an EMF will be induced. And that EMF is the voltage. Okay, now let's take a look at step up and step down transformer. A step up transformer, a transformer consists of primary and secondary coil. We already established this. And then we said the primary coil is the first coil that we made in a transformer. And the second one is the secondary coil, right? So a step up transformer increases the potential difference of the power source. A step up transformer has more turns on the secondary than on the primary. So we make our NS to be greater than our NP. The number of turns, like the one I have here, this is step up. So for step up, we make more turns in the secondary than in the primary. For step up transformer, so we will make our NS, that's the number of turns, NS, the number of turns that we create in the secondary, to be greater than the number of turns in the primary. The number of turns in the secondary will be greater than the number of turns in the primary. So in that case, like the one we have above, like the one we've created above, like this one, if you take a look at this, there are more turns in the secondary than in the primary. So this is a step up transformer. If I want to make a step down transformer, what do I need to do? If I want to make a step down, I will make the turns. If I say step down, okay, let's change the color. If I want to make a step down transformer, I will make the number of turns in the primary to be greater than the number of turns in the secondary. I will make the number of turns in the primary to be greater than the number of turns in the secondary. So I make more windings here, more windings in the primary coil, more windings in the primary side, okay, compared to the secondary. In the secondary side, I make few windings. In the secondary side, I just make few windings. Okay, so this secondary, this is my secondary side of the transformer, this is my primary side of the transformer. This is my primary side of the transformer. So this type of transformer is a step down because you have more turns. That means NP is greater than NS. NP is greater than NS. The number of turns in the primary is bigger than the number of turns in the secondary. So such transformer will reduce the voltage. Let's say if you have 11,000 voltage fed in here, if you have 11,000 voltage fed in from the primary side, then if you bring it down maybe to about 415, you can reduce it to about 415 volts. So you can step it down to about 415 or 230 volts. Okay, so this is a step down transformer. It will reduce the voltage from big number to small number. To reduce the voltage from big number to a small number. So a step up and step down, this is just the difference. For step down, a transformer decreases the potential difference. The potential difference is voltage. EMF is voltage. Potential difference is voltage. I've already said this. Potential difference is voltage. For step down, the transformer will decrease the potential difference. That means it will decrease the voltage. For step up, the transformer will increase the voltage or the potential difference. The transformer will increase for step up, transformer will increase the voltage or potential difference. For example, take a look at this. Look at our step up transformer in the first instance. The voltage was there, potential difference was increased. The potential difference was increased from 11,000 volt to 400,000 volt. You can see the potential difference is increased. Okay, and then we say the number of turns in the secondary is larger than the number of turns in the primary. The number of turns in the secondary is larger than the number of turns in the primary. Okay, you can see the number of turns in the secondary. Number of turns in the secondary. Number of turns in the secondary is larger than the number of turns in the primary. Okay, you can see the number of turns in the secondary is larger than the number of turns in the primary. Is that okay? That's called step up. You're stepping up. Everything secondary is bigger than that of primary. That's a step up transformer. Therefore, a step down transformer, the number of turns in the primary is greater than the number of turns in the secondary. Okay? Now let's take a look at, I think we've explained what you need to hear. I think the next is for us to do some calculation, probably, right? It's to do some calculation. Yeah, let's do some calculation, transformer calculations. Okay, first of all, let's write the equation of transformer. The output potential difference, that's the voltage of a transformer, depends on the number of turns on the primary and the number of turns on the secondary coil. And then the input potential difference. The input potential difference, which is called the input voltage. So the output voltage will depend on these two factors, the number of turns in both primary and secondary, and then the input voltage in the primary. So on that note, we designate our formula. We designate our formula. The popular formula for calculations in transformer is simply given as NS. We have two equations for transformer. Okay, NP over NS. You can start with V or N, anyone. If you start with the VP, then you will write VS on there. Okay, equal to VP over VS. What do we mean by VP, NS? What do we mean? VP is primary voltage in the primary. VS is a voltage in the secondary. Okay, NP is a number of turns in the primary coil, and NS is number of turns in the secondary coil. Is that okay? So this is the first equation for transformer, normal practical transformer. But for an ID transformer, the whole machine is 100% efficient, which is not really in real life. There is no ID transformer in real life. All transformers have heat loss. Okay, when we design a transformer, we expect some losses to take place, to happen. But ID, theoretical, ID is just for theory, for study, for calculation purpose, for theoretical purpose. In practice, there is no ID transformer. There is no transformer that is perfect. Ideal means you say something is perfect. Okay, there is no ID transformer in reality. But we have such calculation. We make assumption and we assume a transformer is 100% efficient. ID transformer means it's 100% efficient. So if a transformer is 100% efficient, you are saying that there is no loss. The power in the primary is equal to the power in the secondary. You're saying the power in the primary, so you can say input power equals to output power. For ID transformer, we say input power. Input means primary side. Input power is equal to output power. For ID transformer, you're saying nothing will be lost. That's why input equal to output. Everything you put into the machine, the transformer, everything will come out. There will be no heat loss. There will be no hysteresis loss. There will be no eddy current loss. There will be no, okay? If input power equals to output power, sorry, I mean to write power. Input power will be equal to output power. But in reality, there's no such thing. Input power means, you know the formula for power. Power is a current times voltage. So in the primary side, you say the primary current is IP. And the primary voltage is VP. IP, VP, because the formula for power, electrical power, not the mechanical power. Not the mechanical power. The electric power, the power is IV, okay? But power loss is I square R. power loss is what? I square R. Okay, this is a loss, heat loss. Heat loss is I square, current square times the resistance in the wire. That's for heat loss. Okay, when there are heat loss, when there is heat loss, the heat loss is in form of power. Okay, when there is heat loss, we say it's equal to I square R. And all these things, they happen in a transformer. There will be heat loss, there will be so many other small losses here and there. That's why we say it's not 100% efficient. But he say in ideal situation, let's assume there's nothing lost. Theoretically, we say IPVP is equal to ISVS. Is equal to ISVS. So these are equation 2 for transformer. These are the only two equations you needed to solve problems in transformer. These are the only two equations. The first one is NP over NS is equal to VP over VS. You can write V first. They say VP over VS equals to NP over NS. You can start with S. You can say NS over NP. If you start with P, both numerator will be P and both denominator will be S. So don't mix them up. Even if you started with S, it means NS over NP is same thing. So someone else might write it like this. You say, oh, this is not how I used to know it. It's the same thing. Someone else might write, if you start with VS over VP is equal to NS. You must write NS. You cannot write NP on top because your V was S. You are starting with secondary. So secondary must also, the number of turns for secondary school, I say secondary school. The number of turns for secondary must also be S, must also be on top. So you say NS over NP. So it's the same thing whether you write it like this, you start with the V, or you start with the N, or you start with the primary N or secondary N. Whichever you want to start with is the same thing. When you solve, you see you get the same answer, it's the same thing. And therefore, ideal transformer, the power, input power equals to output power, which means IPVP equals to ISVS. Now let's take a look at the problem and solve. Let's take a look at a problem. We'll give you the formula. You see here, they say you can start with VP over VS equals to NP over NS, or someone else may start with VS over VP. See, instead of VP over VS, it's now VS over VP. But you must be constant. If you're starting with VS, your NS must also be started first. Okay, so once you have that, then you're good to go. You're good to go. You're good to go. Now let's take a work example, or let's take a problem. Let's write this. A transformer has 20 turns on the primary coil. So I will just write out the values. 20 turns, that's on the primary, that's NP. 20 turns on the primary. Sorry, a transformer has 20 turns on the primary coil and 800 turns on the secondary coil. So they've given us the value. So let's take a look at problem 1. Number of turns in the primary is 20. Number of turns in the primary is 20. So we write them down so that we can solve this. Number of turns in the primary is 20. Number of turns in the secondary, they've given us also 800. This is a step-up transformer because the number of turns in the secondary is way larger than the number of turns in the primary. So this is 800. Number of turns in the secondary is 800. Now let's read the question further. Now, the input potential difference across the primary is 500 volt. Calculate the output potential difference. That's the first part. The input potential difference is what? 500 volt. Now calculate the output potential difference. Input means VP. Potential difference is voltage. Input means the primary side. Okay? So this is 500 volt. 500 volt. 500 volt. Now they want us to find the VS, the output voltage, output potential difference. That's the output voltage. They want us to find VS. So the formula we're using is the first one, not this one, not the ideal situation case. So you can say VP over VS is equal to NP over NS. Okay, so we put the values. VP is 500. So 500 over VS, that's what they asked us to calculate. So we put over VS is equal to, what is our NP? 20. NP is 20. And our NS is 800. So I put the value there, 800. So 800. So the next is for us to cross multiply. The next is for us to cross multiply. Okay. So if I cross multiply, I will get 20 VS. 20 VS. So I get 20 VS. That's if I say this denominator multiplied by this numerator, I get 20 VS is equal to, I cross multiply this and this. 5 times 8 is what? 8 times 5 is 40, right? So I write that 40 here. Say how to multiply without calculator. You put the 20 and this 20, right? So this 0, there are 4 zeros now that we write. 3, 4. So which is 400,000. All right? This 20. Yeah. 8 times 5 is 40. This 40. Then follow with 4 zeros. Right? That's 400,000. So VS is just to divide both sides by 20. This is 400,000 divided by 20. 400,000. 400,000 divided by 20. So 0, this 0 will cancel 1 0. Okay? This 0 will cancel 1 0. Then this 2 goes here, it becomes 2. So I have 20, like 20,000. I have 20,000. VS is equal to 20,000 volts. 20,000, right? 1, 2, 3, 4. 4 zeros. 20,000 volts. And 20,000 volts, we can leave the answer in kilovolts, right? Kilovolt will be 20 kilovolt, meaning divide by 1,000. VS, if you divide by 1,000, it becomes 20. It becomes 20 kilovolts. So whether you leave as 20,000 volts or 20 kilovolt, it's the same thing, okay? You are still correct. It's the same thing, you are still correct. Okay? So that's it. The voltage, you can see it's a step-up voltage. What was it? 500 voltage has been stepped up to 20,000 voltage. That's what a transformer does. That's the wonderfulness of a transformer. That's the good thing about transformer. You put a 500 volt in primary, you raise it to 20,000. You raise it to 20,000. You raise it to 20,000 volts. So a transformer is used for stepping up or stepping down voltages. It's an electromagnetic device that is used for stepping up and stepping down voltages with the operating frequency remaining constant. With the operating frequency remaining constant, right? Okay, so that's the first one. That's the first one, and we've solved it, and we got 20,000 voltage. Now the second part of the question, that's A. Is it state what type of transformer this is? State this is a step-up transformer because it raises the voltage from 500 volt in the primary. It raises the voltage from 500 volt in the primary to a 20,000 volt in the secondary. To a 20,000 volt in the secondary. Remember, any transformer that increases the potential difference from the primary to secondary, if it can increase the potential difference, it's called a step-up transformer. So this transformer is a step-up transformer. So even I don't need to write that, but you just need to know that this is the B part is that it's a step-up transformer. This transformer is a step-up transformer. So these are the type of questions you find in Cambridge exam. Okay, you'll be able to tell, you'll be able to calculate, you'll be able to tell what type of transformer it is. Okay, let's see if they have another question for us. Now they have another question for transformer that is about transformer efficiency, which I've already explained. They said there is no energy loss. The law of conservation of energy says energy can never be lost, or destroyed. Okay, can only be transferred from one place to another, right? So which means the input power equal to the output power. Look at the formula. The VPIP or IPVP equals to IP ISVS or VSIS. So we have given you this formula, and they just give you the formula now, that a transformer that is 100% efficient. And I told you in real life, there's no transformer that is 100% efficient. There's no such transformer that is 100% efficient. We'll come back to this question and we'll solve it. Okay, but before then, let's take a look at this. A transformer in a travel adapter step up a 115 voltage AC mains electricity supply to 230. Okay, so we write that the question number 2. The transformer steps up. Okay, question 2. Let's use the population one, purple color. So a transformer step up. So your VP, our VP is what? 115, right? 115 volts. 115 volts. And our VS is 230. 230 volts. A small adapter transformer. You know, most electronics, they have transformer inside them. Okay, to adjust whatever current you bring into the electronics, design value of current or voltage. Okay, so this questions has given us the voltage in the primary 115 mains and supplies to 230. There's the one in the secondary VS, and needed for a hair dryer. You want to use this transformer in an adapter, you know, the charger adapter. There's a small transformer inside it, and you needed to convert 115 volt to a 230 voltage in your hair dryer. A current of 5 ampere flows through the hair dryer. A current of 5 ampere flow. The hair dryer is the secondary, is the load. The hair dryer is the load. So since current of 5 ampere is flowing through the load, it means that this is IS. This is the current in the secondary. It means this is our IS, current in the secondary side. So I write IS equals to 5 ampere. Equals to 5 ampere. IS, the current in my secondary side, equals to 5 ampere. That's 5A. Okay, they're probably asking us, they want to ask us to calculate the current in the primary. Probably want to ask us. They now, assuming that the transformer is 100% efficient, calculate the current drawn from the main. Current drawn from the main, that's from the source. That's the current in the primary. Remember that. Current in the primary. So we use they want us to calculate the current from the main. Current from the main is our IP, current in the primary side of the transformer. So we don't know. We put question mark there. And the equation we use, remember, input power equals to output power, and our input power is, or main power, current from the main power, which is IPVP, or input power equals to output power, which is ISVS. Or you can start with V. Not only that you start with I, you can say VSIS. Okay? But for me, I write IV. ISVS. Okay. So now we key in our data. That's it. We just put in the information that is given to us. Remember, we're looking for IP. We don't know IP. So we say IP is equal IP multiplied by VP. What's our VP? 115. 115 is equal to, what's our IS? IS is 5 ampere. So you say 5 multiplied by, what's our VS? Our VS is 230. So multiply by 230. So we just make IP the subject. We make IP the subject straight away. So we say IP. So we say IP is equal to 5. IP equal to 5 times 230. Divide by 115. Divide by 115. Divide by 115. 5 times 230 divided by 115. Okay? This 115 can go into 230, right? That would be 2, right? 115 plus 115 is 230, right? 115 plus 115 is 230, right? This plus this is 0, carry 1 is 2. 230. Yeah. So this one go into here, we get 2. 2 times 5, we get 10. So IP is 10, right? So we get our IP, the current in the primary or in the main is 10 ampere. Current in the main is 10 ampere. Current in the main is 10 ampere. So that's the current in the primary side. That's the current in the primary side. You see? 230 times 5 divided by 50, you get 10 as the current in the main. Okay? So our next class will be high voltage transmission.